All right, if you're here for the help session, let's start off on page. Okay, so in class, we're going to finish page 2 in class. So let's try page 4 and 5. Let's see how far we can get with that. Okay, so the graph f consists of the line segments. Let h be the definite integral from 6 to x of f of t. Now, anytime we see this relationship, we know that h and f have kind of a staggered relationship in terms of their derivative and integral. So whenever you see this notation, you have to understand that this f that we're seeing in front of us is really the derivative of h. Okay, that's the relationship here. Okay. So this is the f graph. Is the derivative of h. So we can also think of this as the h prime graph. This is not the h graph, this is the h prime graph. Okay? And this relationship kind of helps establish that. The reason why this f is sitting at the h prime level is because it needs the integral in order to be at the same level as h, which means that f is really not the same level as h, it's really one below. So this is sitting at the derivative level. Okay. Just like before, we want to establish the relationship between h and f. So we know that h is the definite integral from 6 to x of f of t dt, which means that h prime, we know h prime is f, but we can also use second theorem to kind of prove that as well. D over dx, integral from 6 to x of f of t dt. We know these two operations cancel each other out. If I plug x in for t, I get f of x times the exponent's derivative, which is times 1. So we know that h prime is equal to f of x. Right? We've already established that, but we just want to kind of show why that's the case. Okay. So h prime is f. We see that staggered relationship there. And then h double prime then must be equal to what? If I take a derivative level on this side, I need to take the derivative level on this side as well. So the f becomes f prime. Okay, so these are the three relationships here that we're going to be using that's going to help link between the h and the f graph. Okay, so part A says find h of 0. So if I want to find h of 0, I'm just going to use this formula here. The formula says I'm going to replace the upper bound with 0, because that's what the rule says. Now, we want to use the graph to pull this information, but what do you notice about the bounds that makes it a little strange here if we're trying to pull this from a graph? Yeah, this would not be an issue if we had calculus to work through, but if we want to look at a graph, we typically like to read from left to right. It just makes it easier. If we read from right to left, we got to keep track of everything is opposite, right? This is positive, that's negative. All right, this is negative, that's positive. It just feels strange. So I'm going to make it a little bit easier to read. I'm going to flip the bounds. to make it easier for me to evaluate. But if I flip the bounds, I can't just flip the bounds and not change anything, right? What adjustment do we have to make? Make it negative. So let's figure out this piece first, right? We can total of the area and find the region from 0 to 6. So 0 to 6, remember, you're only looking at what's between the graph and the x-axis. Okay, definite integral means that regions above the x-axis is positive, regions below is negative, right? So this is negative 1/2. Okay, I'm just splitting this into easier shapes for me to calculate. This is 1/2 base times height, 1/2 2 times 2. 4 over 2 is 2. Area of this square is 1 times 2, which is 2. Area of this triangle is 1/2 base times height, which is also 2. So then the definite integral from 0 to 6 is just going to be 2 plus 2 plus 2 minus 1/2, or 5.5. Right, we know that the area, the value is 5.5, but then we kept track of this negative, right? So it's going to end up being negative 5.5. Right, it's just tracking that negative all the way through. Okay, how do you guys feel? Yeah, I did negative 1/2 plus 2 plus 2 plus 2. Yeah, negative 1/2. Okay, good. All right, so now part B, find h of 6. Okay, we're back to our definition. What do you think the area or the region is if we're going from 6 to 6? What happens if the upper and lower bound are the same value? It's always going to be what? Always going to be 0, right? Because if we start and end at the same spot, we haven't created any area for us to find. So it's always 0. Okay. Integral from h of 10. H of 10, we use the rule here from 6 to 10. Okay, so 6 to 10. 1/2 base times height. I get 4, but it's below the x-axis, so I need to make this negative 4, right? Okay, any questions so far? Okay, find h of 11. All right, we just keep building off of the rule that they give us here. Okay, we already have 6 to 10, which is negative 4, and we know that 10 to 11 is going to be 1/2 base times height. That's a triangle. That's positive 1/2. So if I total this up, I get negative 4 plus 1/2, which is negative 3.5. Right? Okay, questions so far? Okay, find h prime of 3. H prime of 3, let's find the rule that matches it. H prime of 3 is using the same level as h prime of x, right? So if I want to find h prime of 3, h prime of 3 must be equal to f of what? F of 3, right? We know h prime of 3 is f of 3. We've established that relationship here. So if I want to find f of 3, I simply just look at the order pair, because this is my f graph, right? So what's f of 3? 2, yeah, right there. 3 is 2. Okay, next up, find h double prime of negative 9.5. We know h double prime is talking about f prime of negative 9.5. Or positive 9.5 rather. So 9.5 is somewhere here. That feels like an odd thing to do, having to deal with a decimal value. But, or over here, sorry. But is this asking for the point? It's asking for the what? Okay, what's another word for derivative? Slope. Right, it's asking for the slope at that point. It's okay if it's a decimal value because we know that anything on this line has the same slope. So if I can find the slope of this line, I know the slope at that point. So I just pick any 2 points that I want to go after and just do rise over run. Up 2 over 2. That's a slope of 1, right? Okay, part G, for what value of x is h increasing? So we know that we're staring at the derivative graph. So let's gather all the information from a derivative graph, right? So just like from first semester, we would mark all of our diagrams the same way. Anything above the x-axis is positive slope. Anything below the x-axis is negative slope. Anything on the x-axis is slope 0. So where are the critical points for our h graph? Okay, critical points is where slope is 0. So slope is 0, 1, 6, 10. One, 6, and 10. I also included the endpoints because the graph starts and ends at 0 and 11. So what do you notice between 0 and 1? Positive or negative slope? Well, the slope is showing positive, but where's it located though? It's located below the x-axis, right? So location is going to tell us the slope. Okay, between 1 and 6, above the x-axis. Okay, between 6 and 10, below the x-axis, negative. And then between 10 and 11. Now these arrows tells us how the actual graph is actually moving. It's decreasing to relative min, increasing to relative max at 6, decreasing to relative min at 10. So for what value is h increasing? Let me draw the sine line down here again. Okay, so increasing will be these two intervals, right? 1 to 6 and 10 to 11. Because h prime is positive, greater than 0. Okay, for what value is h prime decreasing? So h prime decreasing, this is really talking about concavity, right? This is not saying when h prime decreasing. So H prime right? H prime is really talking about F, right? When is F going to be decreasing? Let's see, so H prime is decreasing. Decreasing, now we're looking at the slope, right? So decreasing will be from 4 to 8 because F prime or f of x is decreasing, or H prime. This is also H prime, right? We know this is H prime. Or H prime is wait a second here. Okay, H double prime. H double prime is less than 0. So H prime decreasing means H double prime is less than 0. H double prime is really F prime. So when is F prime going to be negative? F prime is going to be negative when we talk about slope, so from 4 to 8. Okay, number 10. Find the absolute extrema. So we're trying to find the points on sorry about the letter here. Find the absolute extrema of H. So this is really extreme value theorem. So extreme value theorem says I can find the highest and lowest points by relying on my critical values, right? So I'll test the endpoints and I'll test any relative max and min that I see. So I need to find H of 0. I need to find H of 1. I need to find H of 6, H of 10, and H of 11. Now we have a nice formula to tell us where to find every point on H, right? Definite integral from 6 to x of f of t dt. Let me write that rule here. I think we've gathered a lot of information from A through D. So let's see what we have, right? H of 0, do we have that? H of 0 is negative 5.5. Okay, so we have that. H of 1, we don't have that yet. Okay, so let's build that. H of 1 is the definite integral from 6 to 1 of f of t dt. I'm just following whatever the rule is telling me to put down. But now I want to read the graph. I want to pull that information from the graph. And if I want to pull information from the graph, what would I prefer from my bounds? The smaller value below and the higher value above, right? So let's flip those bounds and then go to our graph. So 1 to 6, if we look at region from 1 to 6, that's just going to be 6, right? Above the x-axis, we know that's positive 6, but then I'm forcing a negative into this problem here. So this is negative 6. Okay, H of 6, we have that, that's 0. H of 10, we have that, which is negative 4. H of 11, we have that, which is negative 3.5. So EVT says, look at your slope sign line, pull everything that is on the sign line that has a relative max, relative min, or endpoint, and then indicate them as candidates. And now we're just going to look at each of those locations and compare their y values. Whatever has the highest y value is absolute max. Whatever is your lowest y value is your absolute min. So can you find those? What is the absolute max value? What's the highest y value that you see? 0, yeah, that's 0. And then the absolute min is, yeah. So if you were to look at these, if you were to actually graph these points on the h of x graph, these will be the points living on the graph. Okay, so you can expect one of these types of problems on the test on Wednesday. Okay, any questions? Okay, let's look at page 5, and we'll do a Riemann sums problem. Okay, it says estimate the definite integral of v of t dt using the following methods. So anytime we take the integral, our units is going to change. The meters per second is going to rise up to be just meters. Okay, we want to do 6 trapezoids. You guys were able to demonstrate this on your quiz. 6 trapezoids from 0 to 20. So I'm going to indicate all of my subintervals. Find each of the widths. So it's 2, 3, 3, 3, 3, and 3. Okay. Trapezoid has this formula. Width over 2, height 1 plus height 2. And we just total all the trapezoids up. Okay. 2 over 2, height 1 plus height 2, width over 2, height 1 plus height 2, width over 2, height 1 plus height 2. Okay, so we have 3 trapezoids down. We have 3 more to go. That's the interval of 3. My height's 8.5 and 9. That's 6 over 2. And then 3 over 2. Okay. Sum all that up, and I get 155.5. So we're taking the area, right? So if we're taking the area, look at what happens here. You're multiplying meters per second times seconds. Right? The graph is in terms of meters per second. You're multiplying by seconds, so that seconds will go away, and it's just left with meters. Okay, so anytime you're dealing with integral, even if it's an estimation, your units will change, and your units will change by what's happening is that your denominator unit is going to get stripped away. Okay, so meters per second is going to rise up to be just meters. How to get the width? So I got the width the same way that I would find the width on table values. I just subtracted the t values. So 2 minus 0 is 2. 5 minus 2 is 3. 3, 3, 6, 3. All right, you subtract your t values to get the width. And those numbers are all translated up in the numerator of my trapezoid formula. Okay, questions? Okay, we're still going from 0 to 20, but now we're doing 3 left-handed rectangles. So let me redraw my subintervals here. So I need to separate this into 3 subintervals. How about 0 to 5, 5 to 11, and then 11 to 20. Three left-handed rectangles. This is a width of 5. This is a width of 6. This is a width of 9. And then within each subinterval, I want to pick the left height. So this interval has a height of 5, so width times height. Second subinterval has a width of 6 and a height of 7. Third subinterval has a width of 9 and a height of 9. The height of what? Oh, the height comes from the second row. Yeah. And then part number 3, right-handed rectangles. Still 3 rectangles, still the same interval. So we can take all the same width, but we're going to shift over to the height on the right side. So 5 is the width, 7 is the height, 6 times 9, and 9 times 7.5. For this one here? Well, if we're doing rectangles, all we do is we just do width times height. If it's trapezoids, then we have to do width over 2 times height 1 times height 2. So different shapes. Okay, 3 middle rectangles. So middle rectangles, we're just going to pull the middle y value. We're not going to do anything special with it. We're not going to find the average. We just literally whatever is between, doesn't even have to be completely in the middle. It's just whatever lands somewhere between 5 and 7. If they give that to us, then we'll take that value. So width times height, width times height, width times height. Okay, it's just a coincidence that 6 trapezoids and 3 middle rectangles are the same value. Okay, just kind of a coincidence there. Okay, questions with that? Okay, part B, find the average velocity. So average velocity, this is average value theorem. A and B value. So we have this, right? We have this depth integral from 0 to 20 of v of t. Pull that from part A. Average velocity. .775 meters per second. Okay. Okay, let's do a particle motion problem here. This is page 9. Okay, so it says particle moves horizontally so that its velocity at time t between 1 and 9 is given by a differential function. That just means that's a smooth curve. Velocity is 0 at 1, 3, 7, and 9. This is the velocity function. And then there's horizontal tangents at 2, at 5, and at 8. Okay, so we know that these are 2, 5, and 8. Okay, the areas are given. This is an area of 2. That's just a coincidence that number is there here. This is an area of 3, and this is an area of 6. Okay, create sine lines for v of t and a of t. So velocity, this is the velocity graph. So this is negative velocity, positive velocity, negative velocity. Critical points is where velocity is 0. Okay, acceleration is the slope of velocity or the rate of change of velocity. And now we look at the slope, right? So the critical points for acceleration is where the slope of velocity is 0. So 2, 5, and 8. Negative slope of velocity would tell us where acceleration is negative. Positive slope is kind of like concavity, tells us where acceleration is positive. 5 to 8, negative slope. 8 to 9, positive slope. Okay, part B. On what interval is the velocity negative? Okay, so velocity is negative in these intervals here, right? 1 to 3, 7 to 9. Simply because my velocity is less than 0. Okay. On what interval is acceleration positive? Well, we can see it here, right? 2 to 5 and 8 to 9. Okay, part D. On what interval is the speed of the particle increasing? Okay, so speed of the particle increasing or decreasing. We want to know whether the signs are the same or different, right? So if we look at 5 to 7, right, everything is, I try to line everything up here. So 5 to 7, negative acceleration, positive velocity, the signs are different. So speed must be decreasing. Between 7 and 8 is the speed increasing or decreasing. So 7 and 8. So 7 to 8, 7 to 8 is negative, 7 to 8 is also negative. So signs are the same. Speed is speed is increasing. Okay, find the position of the particle at t equals 3. So now we're looking at specific location. We know position is involving the antiderivative, but this is specifically involving the formula here. Final position is equal to initial position plus displacement. So if I want to find any position, I need to have a starting location plus however much progress I made in that interval. Okay, so look at what's given to us. We have x of 1 equals 2. That is my starting point. Okay. So if I want to find x of 3, I need to start at x of 1. And I need to figure out how much progress did I make my displacement between the two time intervals. X of 1 is 2. Definite integral from 1 to 3 of v of t. We see that this is going to be negative 2, right? So we know in this interval, this particle is going to move 2 units to the left. That's what it says here. The area under the graph are 2, 3, and 6. Right? So we know this is, he's going to move 2 units to the left. Here, he's going to move 3 units to the right. And here is going to move 6 units to the left. This is how much progress he makes. The area involved between the graph, velocity graph, and the x-axis tells us how much he actually moves. Okay, so 2 plus -2. He's going to start off at location 2. He's going to backtrack 2 units. He's going to end up at location 0. Okay. If I want to find x of 7, again, I can start off at x of 1 and then just total my progress between 1 and 7. So again, x of 1 is 2. And then now I need to figure out the sum from 1 to 7. So -2 plus 3 is going to be 1. Okay, x of 9. Again, I want to start at 1, and I want to map my progress from 1 to 9. Okay, 1 to 9. -2 plus 3, that's 1. 1 minus 6 is -5. Okay, find the absolute extrema. This is extreme value theorem. So we just need to find endpoints and critical points based off the velocity graph. So we'll find the position at 1, 3, 7, and 9, which we have all in front of us. So we can just use those values. Because these are all candidates. Okay, absolute max is 3, absolute minimum is -3. Okay, find the total distance. Total distance is just the absolute value of v of t dt. Remember, total distance, we don't add any starting point. It's just the absolute value of v of t. So from 1 to 9, we just treat everything like a positive number. 2 plus 3 is 5. 5 plus 6 is 11. Okay, displacement from 3 to 9. We just keep track of the positive and negatives. So 3 to 9, 3 minus 6 equals -3. Okay, to sketch the graph, we have a bunch of order pairs, so let's just plot all those order pairs that we have in front of us. One, 2, 3, 0, 7, 3, and 9, -3. Okay, based off of the velocity sign line, we kind of have an idea how the graph is going to move. From 1 to 3, it's going to be decreasing. From 3 to 7, it's going to be increasing. From 7 to 9, it's going to be decreasing. Okay, but we also have these points of inflection along the way, right? At 2, at 5, at 8. So just mark off where you think those values could be. Because you know that these are going to be the target points where the concavity is going to change, right? So here we're going to start off with concave down, followed by concave up, followed by concave down, and finally end up with concave up. Okay. All right, so we can pick up tomorrow morning with some of the other worksheets that we're not going to be able to get to in class. So in class, we're going to do page 2 and 3. But then tomorrow, maybe I'll try 7 and 8 in our help session. Okay. Thanks. Any questions? Mm-hmm. 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 Yeah, okay. These two, we're just using approximation, so there's not a whole lot of, we don't use any calculus features there. But which one do you want me to do? Show me how. Okay, so this is my velocity function, t sine t squared. Let's go to y1, and I just enter that in as x sine x squared. Okay. I want to find the velocity at 1.5, so if I go back to my home screen, I do bars, y bars, function 1. So this y1 right now, I stored that x sine x squared there. I want to find the velocity at 1.5, so I just plug in 1.5. So it's going to take 1.5, it's going to insert it to all the key values of my velocity. Thank you. Okay, take care. Yeah, the parentheses right here. Right? Okay. The parentheses has to be, see that? The squared is inside. That's outside is going to change the value. Test, like, are we going to have to use the calculator? Yeah, because the calculators, otherwise you have to do the calculus by hand. You have to do product rule, you have to do substitution. It's a lot faster than the calculator. Okay, so this is, acceleration is the derivative of velocity. So we have a feature here, math 8, which is derivative. So I can find the derivative of this function. So I have it again stored under y bars, y1. So I want to find the derivative of my velocity at 1.5. So what's going to do is it's going to take 1.5, it's going to insert it into the derivative. It's going to spit out acceleration value for you. And then final position equals initial plus displacement, and then I can plug this in the calculator. So that's math 9. Math 9 is your definition. So you're just matching whatever you have on paper into the calculator. So integral from 0 to 2. That's my velocity function. So bars, not bars, function. Thank you. Yes. Initial position, right? Initial position is your starting point, which is. Does it say? Yeah, that's it. Yeah. So it's 3 plus 0.826, which is 3.826. And the distance is the absolute value. So you do 9, 0, 2. So we have to all the. Yeah. Right. And then absolute value is number ADS. And type in the function. So I have it highlighted in these steps here.
And this is just what we did.
Yeah, so there's my derivative steps. This is the integral steps. And here's the step. Yeah.
There's only these 3 questions.
Yeah, particle motion, Riemann sums, and then a graph.